We have spent a few videos talking about summation of vectors. So now let's move on to how to multiply vectors. Okay, so when we multiply a vector, we can multiply a vector with a scalar, or we can multiply a vector by another vector. Okay, if it's multiplying with a scalar, we call it scalar multiplication. If it's multiplying by another vector, we call it vector multiplication. Okay, in this video, we are going to focus only on scalar multiplication. So I'm going to give you two examples involving scalar multiplication, and I hope you are able to get an idea what is scalar multiplication and what are its characteristics. So net force, it's one of the example where it involves scalar multiplication. As you can see here, we have a vector, which is acceleration, a vector quantity, and we multiply it by mass, which is a scalar quantity, and we get the resultant force, or the net force, as the result of the multiplication. And as you can see here, because this net force has a right arrow on top of it, we know that the result of this multiplication is a vector. Okay, let's look at another example. Another example that we have here is restoring force of a spring. Okay, the formula is like this. F is equals to negative kx. As you can see here, x is a vector, and negative k here is the spring constant. Spring constant, there's no direction to it, so it's just a scalar value. And if you multiply a vector with a scalar, the result of our multiplication is a vector. Okay, so this is the first characteristic that we can see. If you multiply a scalar with a vector, the result of the multiplication will be a vector. Okay, now let's move on to investigate deeper these two concepts that I'm going to talk about. For net force, we can imagine we have a block with mass m lying on the ground like this. Then, if this mass is undergoing an acceleration in this direction, okay, either it's moving in this direction and speeding up, or it's moving in that direction, moving to the left while slowing down. Okay, if it's accelerating to the right, there can be two possibilities. Either it's moving to the right with increasing speed, or moving to the left with decreasing speed. Okay, but let's don't deal too much about this. This will be chapter 2. But if we have an acceleration pointing to the right, we know that this acceleration must be caused by a net force pointing in the same direction. The acceleration vector and the net force vector should be in the same direction. Because if you want to speed things up to the right, of course you have to push to the right. If you want to slow down something to the left, something is moving to the left and you want to slow it down, you have to push to the right to slow it down, right? Well, it's still logical at this point. Okay, so we can see that A and net force must be in the same direction. Now let's move on to restoring force. If we talk about restoring force of a spring, let's say today I have a spring here which is not stretched, which is not compressed. So we can say this spring here is at its equilibrium length, and this spring here has a spring constant K. That one is fixed. Okay, as long as you don't change the spring, you won't change the K. The spring, if it's the same spring, the K will be the same. Now we call this the original length of the spring, or the equilibrium length. And now, if we happen to stretch our spring to the right, to another new length, then the amount of stretch that we incur on this spring, we have a vector called x to represent it. So in this case, it's been stretched to the right. So our vector x here is pointing to the right. Okay, so if we talk about restoring force is the force that the spring exerts to restore back to its original length. So if the spring wants to get back to its original length, it will want to pull towards the left. Okay, it's been stretched to the right, but to restore it, the spring will want to pull itself back together, so it will pull itself back to the left. Okay, so the force is, the restoring force of the spring is to the left. Okay, it's actually trying to counter the pulling force. Let's say I'm pulling using my hand to the right. The restoring force is trying to counter the pulling force. If the pulling force is to the right, the restoring force will be to the left, because it wants to restore back to the original length. Okay, now we see here the x, which is the displacement from the original length. Okay, displacement from the original length, original position. Initially the n is at here, now the n is at here. The displacement is to the right, but the restoring force is to the left. Now you see they are in opposite direction. Now, what kind of conclusion am I trying to make here? If you notice here, the mass that we have here is actually a positive value. At our level, all mass are positive. Okay, you won't encounter any negative mass. Okay, so in this case, our scalar is a positive scalar value. But for this second case over here, our scalar value here, it's a negative. K is always positive, but multiplying with a negative, it will become a negative scalar value. So you can see here, if our scalar is positive, the result of the vector out from the result of the scalar multiplication, you have the same direction as the initial vector. Okay, so the conclusion I'm trying to make here is, if the scalar is a positive value, the direction remains the same. Initially it's pointing to the right. After multiplication, it's also pointing to the right. If it's a negative value, like this negative k here, then the direction is flipped to the opposite. Initially, the x is to the right, but after this scalar multiplication, the result of the multiplication will be pointing in the opposite direction, which is to the left. So this positive and negative scalar value is very important for us to determine the direction of the result of the scalar multiplication. So that's a basic overview on scalar multiplication. In the next video, we'll move on to vector multiplication.